Jean-Baptiste Joseph Fourier was born in the city of Auxerre, France. One of 12 children, Fourier quickly showed great promise in the field of mathematics. By age 21, Fourier desperately wanted to make a name for himself in the math world. However, France has other plans, putting Fourier's mathematical concerns on hold. It's 1799, and Fourier gets a knock on his door. It's Napoleon. He wants Fourier to take up a role in the new French government. Fourier will serve in various governmental positions, whether he wants to or not, for most of the rest of his life. In 1804, Fourier begins his memoir on the propagation of heat in solid bodies, and by 1807, he had finished his rough draft. Fourier gets another knock on his door. It's the French Academy. They tell Fourier that they have created a bounty for the best work on research of heat dispersion.
Oh, j'ai exactement ce qu'il faut.
Exclaims Fourier. Spurred on by the bounty, Fourier continued to improve his theories, submitting his memoir and winning the contest in 1812 with the work we still study today. One of the more widely known aspects of Fourier's work is the creation of the Fourier Series. But what is the Fourier Series, and how do we solve for it? Get ready, because this is a lot of math in a short time, but I know you can do it. The Fourier series describes a way to create some periodic function, f of x, as the sum of sine and cosine waves. Fourier first used the series to study heat dispersion on a metal bar, but any equation works. Assume the equation f of x equals a of 0 plus a of 1 cosine pi x over L plus b of 1 sine pi x over L plus a of 2 cosine 2 pi x over L plus b of 2 sine 2 pi x over L, and so on and so forth. Here, it is important to note that a of 0 has no relation to a of 1 or a of 2, and the same can be said for the b terms. Using our knowledge of summations, we can rewrite the equation of f of x to a of 0 plus the summation of n equals 1 to infinity of a of n cosine n pi x over L plus b of n sine n pi x over L. This is cool and all, but how do we find the a of n and b of n values we need to construct f of x? Before continuing to solve for the Fourier series, let's cover 3 important things that will aid us later on. This symbol is an integral. For our purposes, we just need to know the meaning of the integral between negative L to L of f of x dx. All this tells you to do is calculate the area between the curve and the x-axis from negative L to L. Area under the x-axis is considered negative area and is subtracted from the area above the curve, which is considered positive area. If I were to integrate this function from negative L to L, for example, I would get 1. Second, if we were to use this integral on an odd function, the result will always be 0. Because f of negative a is equal to negative f of a for any odd function, the accumulation of area from 0 to a for this function will then be cancelled out by the sum of the area from negative a to 0. Just take a look at the sine function. Third, if we use this process on cosine n pi x over L, or sine n pi x over L, assuming n is a non-zero integer, the result will always be 0. This is because, for a full period of a sine or cosine function, the area over and under the curve will always be equal. I'll save these 3 rules in the corner if you need them. Okay, back to our equation. How do we find the right a and b values? Let's start by finding our a's. First, I'm going to multiply both sides of the equation by cosine m pi x over L, where m is some positive integer. Multiplying the equation by this expression will create this. Notice, because of our summation rules, we can put the cosine m pi x over L inside the sigma, as it is a constant. Next, I will integrate both sides from negative L to L. Now, our equation looks a little wonky, but it will work out. Once again, I can distribute the integrals inside of the sigma. Here is where the magic happens. By our third rule, the first part of the equation is 0. It can go away now. Additionally, we have learned that an even function times an odd function equals an odd function. Therefore, cosine of m pi x over L times sine n pi x over L is an odd function. So, by our second rule, it is also equal to 0. Alright, our equation is looking much simpler now. we only have one term left in the summation to get rid of. Sadly, our three rules won't help us here, yet. Notice cosine of n pi x over L times cosine of m pi x over L is kind of similar to our cosine rules for cosine of a plus b and cosine of a minus b. If we add cosine a plus b and cosine a minus b, we get 2 times cosine a times cosine b. Half that, and we get cosine a times cosine b. Now that's just like what we have. Converting our cosines to this form, we end up with this. Due to our third rule, cosine of n plus m times pi x over L, half of our new equation can now turn into 0, as n plus m is always going to be a non-zero integer. Cosine of n minus m times pi x over L is similar, as n minus m will always fit our third rule, except for when n minus m is equal to 0. In that case, our function will be equal to 1, as cosine of 0 is equal to 1. So, if we can take out all of our cosine n plus m terms, and all but one of our cosine n minus m terms, we can finally get rid of the pesky summation, and are left with this. Since the integral between negative L to L of 1 is 2L, we can further simplify like this. Lastly, we can just bring the L to the other side in order to find the A of n. Solving for the B of n is done in basically the same way, and we can rinse and repeat this equation for different n values to find more A of n and B of n values. The more time you do this process, the more accurate your new equation becomes. Alright, we've looked at Fourier, and we've looked at a series. Now it's time to look at the cool uses of the series. The Beatles have this popular song, A Hard Day's Night, and people are having trouble figuring out how the iconic beginning chord was played. One day, a mathematician decides to use the Fourier transform in order to deconstruct the big jumbled sound wave into many sine and cosine waves, each representing a different note on a different musical instrument. Putting each note together, the mystery chord was pretty accurately recreated. Another use of the Fourier series is in science. Let's say you're publishing a paper on the breathing patterns of angry birds. When studying one particular bird, you find its breathing very irregular, following no specific pattern. All you have to do is use your trusty Fourier series, and boom, you have a pretty accurate representation of bluebirds' breathing for curious readers to study further. That's everything I have time for.
Au revoir.